A black hole could shred you into atoms before you even saw it. This is the reality of the universe's most extreme environments, places where the ordinary laws of nature break down. We are going on a journey through 25 facts about these cosmic wonders, from worlds with oceans of boiling fluid to stars with magnetic fields so strong they could wipe a planet clean from half a galaxy away. By the end, you will understand the fundamental forces that shape reality in its most violent and beautiful forms. We will see how diamonds rain from alien skies and how entire planets wander in eternal darkness. What single idea about the cosmos feels the most impossible to you? The first stop on our tour of cosmic extremes lies just 40 light-years away, orbiting a dim red dwarf star. Gliese 1214b is a world entirely consumed by water, a planet-wide ocean not hundreds of meters deep, but hundreds of kilometers. To stand on its hypothetical surface, if it even has one, would be to stand at the bottom of an alien abyss with pressure over 1,000 times greater than the deepest trenches of Earth's oceans. This is not the refreshing blue water of our world. Here, the planet's close orbit to its faint sun cooks the entire global sea to temperatures reaching hundreds of degrees Celsius. At those insane pressures and scorching heats, water enters a state alien to our experience, becoming a supercritical fluid. In this churning, hellish broth, the familiar line between liquid and gas vanishes entirely. The ocean itself boils, but it cannot form bubbles or steam as we know it. Instead, it exists as a single, seething, corrosive substance, more like a dense, hot fog with the weight of a crushing liquid. The chemistry in such a stew is unimaginable, with minerals and compounds dissolved in ways that defy earthly logic. For life as we understand it, this environment is a realm of pure destruction, where complex molecules would be ripped apart by the relentless energy and pressure. Yet Gliese 1214b presents a profound question. If life can emerge in the scalding vents at the bottom of our own oceans, what truly impossible chemistries might be simmering in that global, supercritical cauldron? It is a reminder that the universe's idea of an ocean can be far stranger and far more violent than anything we have ever dreamed. Yet the crushing pressures of a water world are just a prelude. Travel further out to the cold, dim reaches of our own solar system, and you will find a weather phenomenon of breathtaking violence and bizarre beauty. Deep within the ice giants Neptune and Uranus, scientists believe it literally rains diamonds. This is not poetic metaphor, but a stark prediction of planetary physics. The atmospheres of these distant worlds are rich with methane, a simple molecule of carbon and hydrogen. As you descend through thousands of kilometers of thick, slushy atmospheric ice, the pressure becomes unimaginable, millions of times greater than Earth's surface. At these depths, the relentless squeeze rips the methane apart. The hydrogen is liberated, floating away, while the raw carbon atoms are crushed together. Under that incredible planetary weight, the carbon is forced into the crystalline structure of diamond. And so, in the eternal darkness of these planetary interiors, a glittering hail begins to form. These are not delicate gemstones, but likely chunks of solid diamond, perhaps as large as icebergs, falling through strange oceans of superheated water and ammonia. Scientists have actually recreated a tiny piece of this process in laboratories on Earth, using powerful lasers to shock hydrocarbons and generate the fleeting, immense pressures needed to forge nanodiamonds. The experiments support a stunning conclusion. While we gaze at the serene blue faces of these planets from afar, their hearts are engaged in a continuous, slow-motion storm of crystallized carbon, a precipitation of immense wealth in an environment where it means absolutely nothing. It is a perfect example of the universe's alien logic, where conditions of terrifying extremity create something we consider precious in a place forever beyond our reach. But even the diamond rains of Neptune occur within the warm embrace of a star. To find a deeper, more profound darkness, you must leave solar systems entirely. Drifting alone in the infinite black between stars are rogue planets, worlds violently ejected from their birthplaces by gravitational chaos. These are eternal exiles, and their environment is the most desolate imaginable. Without a sun, there is no day, only an unbroken, absolute night that has lasted for billions of years. The temperature on their surfaces plummets to just a few degrees above absolute zero, the coldest temperature possible in the universe, where all atomic motion nearly ceases. It is a silence and a cold so complete it defies human comprehension. Yet, within this frozen tomb, a flicker of possibility remains. Many of these wandering worlds, especially larger ones akin to Jupiter or Neptune, could retain immense heat from their violent formation, locked deep within their rocky cores. This internal furnace, a faint geothermal glow, might be enough to sustain a secret. Beneath a crust of ice perhaps hundreds of kilometers thick, a vast global ocean of liquid water could persist, completely insulated from the frozen void above. Imagine such a place, a sea that has never known sunlight, where the ceiling is a planet-spanning sheet of ice, and the only warmth comes from the slow radioactive heartbeat of the planet's core. In that eternal, pressurized darkness, life would have to be utterly alien, thriving on chemical energy from hydrothermal vents on the ocean floor, never evolving eyes, never conceiving of a sky or a star. Its entire universe would be that dark, hot abyss. This speculative biology presents one of the most haunting questions in astrobiology. Could life be more common in these lonely, sunless oceans than on the Earth like worlds orbiting stars? It suggests that the spark of life may not need a golden sun, but only a source of energy and a pocket of liquid, hidden in the deepest, darkest corners of the cosmos. The desolate journey of a rogue planet is one of quiet exile, but the galaxy can also expel its children with unimaginable violence. Far above and below the familiar spiral disk of our Milky Way, in the sparse galactic halo, there are stars moving so fast they are essentially unbound. These are hypervelocity stars, and they are cosmic bullets fired from the most powerful gun in existence, the supermassive black hole at the galaxy's heart. The process is a brutal demonstration of celestial mechanics. When a binary star system, two stars orbiting each other, drifts too close to the galactic center's immense gravity well, the central black hole can perform a gravitational slingshot of catastrophic precision. It captures one star into a tight orbit, while violently flinging its companion away at speeds exceeding 1 million miles per hour. In an instant, that star is liberated from its partner and ejected from the galactic core entirely, shot out on a one-way trip into the void. Its new environment is one of supreme isolation. It streaks through the near-perfect vacuum of intergalactic space, far from the dense clouds of gas and dust that populate the galactic disk where new stars are born. This star carries its own light and heat, but it travels in a profound and permanent solitude, leaving the shimmering city of the Milky Way behind for an endless, dark frontier. Without the protective magnetic fields and relative crowding of the galactic disk, it also faces the full, unfiltered barrage of cosmic radiation from all directions. Any hypothetical planets that survived this explosive birth would orbit a sun bathing them in intense radiation while offering a sky with almost no other stars, just the fading glow of their abandoned home galaxy receding forever into darkness. These stars are not wandering aimlessly, they are fleeing, and their trajectory writes a permanent record of a violent encounter that happened millions of years ago. They are the undeniable proof that even stars are not safe from the disruptive chaos at the heart of creation. The loneliness of a hypervelocity star is profound, but it pales before the sheer, crushing density of a dead sun's corpse. A neutron star is what remains after a massive star explodes in a supernova, its core collapsing under its own weight. All the mass of our Sun, over 300,000 times the mass of Earth, is compressed into a perfect sphere no wider than a city. The gravity on its surface is so strong it bends light itself, and a single sugar cube of its material would weigh over 1 billion tons here on Earth, as much as a mountain. This incomprehensible density creates a surface environment unlike any other. The neutron star's crust is not made of rock or ice, but of a rigid lattice of atomic nuclei packed together tighter than in any substance we know. The electrons have been forced into the protons, turning everything into a sea of neutrons, and the outer layer crystallizes into a material harder than diamond by a factor of 10 billion. This crust, however, is not a serene shell. The star's immense magnetic field, trillions of times stronger than Earth's, grips this crystalline skin with titanic force, warping and stressing it over time. The strain builds until the entire crust suddenly cracks and shifts in a stellar earthquake, a starquake. The energy released in that single seismic event is staggering, equivalent to the total energy output of our Sun over 100,000 years, all unleashed in a fraction of a millisecond. This crack in the hardest known material in the universe triggers a flash of gamma rays and X-rays that can be detected across interstellar space. A brilliant scream from a world where a piece of dust falling to the surface would strike with the force of 1,000 hydrogen bombs. It is a landscape where solid matter exists at the very edge of possibility, perpetually on the verge of shattering under its own impossible weight. Yet beneath that unbreakable crust lies an even stranger reality. The neutron star's interior is not simply solid all the way through. At its heart, under pressures that make the crust seem fluffy, physicists predict a quantum environment so alien it defies all intuition. Here, the neutrons themselves may break free of the rigid lattice and flow together as a superfluid. Imagine a liquid with absolutely zero viscosity, no friction or stickiness at all. A superfluid can climb the walls of its container, leak through pores smaller than an atom, and once set in motion, it could theoretically swirl forever without losing energy. This is not science fiction, but a state of matter we can create in labs with ultra-cold atoms. Inside a neutron star, this superfluid sea of neutrons would exist at temperatures of millions of degrees, a hot quantum soup spinning at the heart of a cosmic tomb. And this is where things get truly wild. When this frictionless fluid rotates, it cannot spin like a normal liquid. Instead, it must break into a vast array of microscopic whirlpools called quantum vortices. Billions upon billions of these tiny tornadoes, each thinner than an atom but carrying immense rotational energy, would align like soldiers along the star's axis of spin. The rigid crust above is locked to this superfluid whirlpool beneath, and together they define the neutron star's incredibly precise rotation, often ticking like a perfect cosmic clock. But sometimes the clock stutters. The vortices in the superfluid, normally pinned to the crust, can suddenly break free and surge outward in a collective rush. When this happens, the star's rotation experiences a glitch, a tiny but measurable speed up in its spin. In an instant, a millisecond pulsar can spin a fraction of a second faster, releasing more energy than our Sun emits in a week. This is the ghostly fingerprint of a quantum phenomenon playing out on a stellar scale. A storm of microscopic whirlpools deep inside the densest object we know momentarily unpins and changes the spin of an entire star. It means that within these ultra-dead, ultra-dense remnants, the bizarre rules of the quantum world are not just present, they are in command, orchestrating events that ripple across the light years. The quantum storms within a neutron star are confined to a city-sized sphere, but to witness energy on a truly cosmic scale, you must look to the center of an entire galaxy. Here, hidden in the brilliant core of what astronomers call an active galactic nucleus, lies the universe's most powerful engine. A supermassive black hole, weighing millions or even billions of times our Sun's mass, is not passively consuming matter. It is a frenzied, spinning dynamo, and its byproduct is a spectacle of pure violence. As vast rivers of gas, dust, and even entire stars spiral into the black hole's gravitational well, they do not fall straight in. Instead, they form a seething, flat disk of superheated plasma called an accretion disk, whirling at relativistic speeds and glowing with the light of a trillion stars. This is not the end of the story, but the beginning of a celestial launch sequence. The black hole's immense spin, coupled with magnetic fields of unimaginable strength that are twisted into coils by the disk's rotation, acts like a cosmic railgun. Along the black hole's polar axis, perpendicular to the disk, these forces focus and channel a small fraction of the infalling material. What emerges are the relativistic jets, two opposing beams of magnetized plasma fired at over 99% the speed of light. The environment within one of these jets is a realm of extremes that defies any earthly comparison. The particles inside, mostly electrons and protons, are accelerated to energies billions of times greater than anything produced in our largest particle colliders. Magnetic fields within the jet, trillions of times stronger than Earth's, whip these particles into spirals, causing them to scream across the electromagnetic spectrum in a brilliant synchrotron radiation. Temperatures soar to levels where matter exists only as a dissociated soup of fundamental particles. These jets are not brief flashes, they are sustained eruptions that can blaze for millions of years, stretching far beyond their host galaxy into intergalactic space. They can plow through the sparse gas between galaxies for hundreds of thousands of light years, forming colossal lobes of radio emission that are among the largest single structures in the entire observable universe. To stand in the path of such a jet, even from a distance of 1,000 light years, would be to experience an apocalypse. The intense radiation and particle bombardment would sterilize any planetary system, stripping atmospheres and boiling away oceans in an instant. These jets are the universe's ultimate signposts of raw power, proving that even the darkest objects, the black holes themselves, can sculpt the cosmos on the grandest possible scale, lighting up the void with beams of energy that cross intergalactic distances. While galactic jets reshape the cosmos, a world of more intimate, simmering fury exists right next door. Venus is Earth's twisted sibling, a planet of almost identical size and composition that took a horrifically different path. Its surface is not a rocky landscape under an open sky, but the floor of a planetary pressure cooker. The atmosphere here is 92 times thicker than Earth's, a dense, toxic soup of carbon dioxide. Standing on Venus would feel like being submerged under 900 meters of ocean water, a pressure that would instantly crush a submarine, and that crushing weight is paired with a heat that defies earthly comparison. The surface bakes at a constant 467 degrees Celsius, hot enough to melt lead, to cause zinc to flow like water, and to make most electronic components fail in seconds. This hellish temperature is the result of a runaway greenhouse effect, where the thick atmosphere traps solar energy with terrifying efficiency, turning the entire planet into a uniform, searing furnace. High above this scorched ground, the sky is not blue, but a perpetual, gloomy orange, obscured by clouds not of water vapor, but of concentrated sulfuric acid. These clouds rain acid, but in a final, cruel twist, the droplets evaporate from the intense heat long before they can ever reach the surface, creating a virga of corrosive mist in the upper atmosphere. For decades, this environment was considered utterly impenetrable. Then, in the 1970s and 80s, the Soviet Union's Venera program achieved the impossible. Their spacecraft, built like titanium diving bells, plunged through the acidic clouds and endured the immense atmospheric pressure during their descent. A handful actually reached the surface and survived. The Venera landers, heroic machines designed for a suicide mission, operated in this crushing, corrosive hell for mere minutes, some for just over an hour, sending back the first and only direct images we have from the Venusian surface. Those grainy, color-tinted photographs show a stark, rocky desert under a diffused orange sky. a world where every component was screaming against the heat and pressure until it finally fell silent. They proved that even in the most hostile environment in our solar system, human ingenuity could, for a brief and glorious moment, plant a flag. Those images are a testament to a world that took all the ingredients for an Earth-like planet and forged them into a permanent global inferno, a warning of what can happen when a climate spirals completely out of control. While Venus is a world of scorching atmospheric pressure, the outer solar system holds a different kind of secret, locked away under a shell of ice. Orbiting Saturn, the small moon Enceladus appears as a brilliant white marble, its surface reflecting almost all the sunlight that touches it. This is not a dead, frozen ball, however. At its south pole, great fissures known as tiger stripes scar the landscape, and from these deep cracks the moon is singing. Enceladus is erupting, but these are not volcanoes of fire and lava as we know them. They are cryovolcanoes, and they erupt with a chilled fury. Instead of molten rock, they spew towering plumes of water vapor, ice particles, and complex organic compounds like methane and ammonia. These geysers blast hundreds of kilometers into space, a shimmering fountain against the blackness, feeding one of Saturn's faint outer rings. The energy for this astonishing activity comes from the immense gravitational squeeze of Saturn itself. As the moon orbits, Saturn's tidal forces flex and knead its interior, generating enough heat to maintain a global, salty ocean trapped between its rocky core and its icy crust. Those plumes are a direct vent from that hidden sea, a sample of an alien ocean ejected into the vacuum for us to study from afar. When the Cassini spacecraft flew through these plumes, its instruments tasted the spray, detecting not just water and organics, but tiny grains of silica that could only form in hot water interacting with rock on the ocean floor. This was the smoking gun. Enceladus has hydrothermal vents on its seafloor, environments strikingly similar to those on Earth where life thrives in complete darkness, powered by chemistry rather than sunlight. The environment within that ocean is one of perpetual night under crushing pressure and near freezing temperatures, yet it is rich with the essential ingredients and energy sources for life. It is a dark, cold, water-rich world that may be one of the most habitable places in our solar system, not despite its extremes, but because of them. Enceladus is not alone in this cryovolcanic whisper. Jupiter's moon Europa, slightly larger and with a cracked, icy shell resembling a cracked egg, shows similar promise. Its smoother surface suggests a more active geology, where the ice crust is constantly being recycled from below, and Hubble Space Telescope observations have glimpsed what appear to be sporadic water plumes as well. Together, these moons present a profound shift in our understanding of habitable zones. Life may not need a planet orbiting at the perfect distance from a star. It might instead flourish in the lightless abyss, warmed from within by the gravitational embrace of a giant planet, its story written not on a sunlit surface, but in the chemistry of icy plumes against the stars. That dark, warm ocean beneath the ice of Enceladus is a hidden sanctuary, but some cosmic storms rage in plain sight for anyone with a telescope. Jupiter's Great Red Spot is not merely a storm. It is a planetary-scale hurricane that has been churning for at least 350 years and likely far longer. To call it a storm is almost an insult. This is a permanent, violent, atmospheric maelstrom wider than our entire planet, a self-contained engine of chaos in the banded clouds of a gas giant. Its winds scream at speeds exceeding 400 miles per hour, making the most powerful Category 5 hurricane on Earth seem like a gentle breeze. This vortex is so vast that if you could stand on Jupiter's cloud tops at its edge, you would not see the other side. The curvature of the storm itself would block your view, a brick-red wall of churning ammonia and water ice stretching into the sky. The very source of its iconic color remains one of solar system science's enduring puzzles. It is likely a complex cocktail of chemicals, perhaps sulfur or phosphorus compounds dredged up from the deeper layers of Jupiter's atmosphere by the storm's immense churn, and then altered by the fierce ultraviolet radiation from the distant sun. The spot is not static. It has been shrinking and changing shape for decades, but its core persists, a colossal, spinning plug of gas held in place by the jet streams that race around it. And this is the central mystery, its longevity. On Earth, hurricanes are fueled by warm ocean water and quickly die over land. Jupiter has no land, and the great red spot's energy does not come from a sun-warmed sea, but from the planet itself. The storm is believed to be a towering thermal chimney, drawing heat from Jupiter's incredibly hot interior, thousands of degrees below the visible cloud decks. This internal furnace, left over from the planet's formation, provides a continuous, if indirect, power source. The storm is also a feature of pure fluid dynamics, a stable vortex in the shear between two of Jupiter's opposing jet streams, a kind of atmospheric traffic jam that has become self-perpetuating. It is a world within a world, a chaotic, violent environment that has outlasted every human empire, a testament to the fact that in the cosmos, weather is not just a passing event, it can be a permanent, roiling feature of a planet's very identity. The fury of Jupiter's great red spot is a storm of atmosphere, but the cosmos harbors magnetic tempests of an entirely different order. If a neutron star is a city-sized diamond, a magnetar is that same object twisted into the most powerful magnet in the known universe. These are the remnants of the most massive, rapidly spinning stars, and their magnetic fields are not merely strong, they are apocalyptic. A magnetar's field can be 1 quadrillion times more powerful than Earth's protective magnetic shield. This number is so vast it loses meaning, so consider the effect. Within a few hundred miles of a magnetar, the magnetic force becomes so intense it does something unthinkable. It warps the very structure of matter. The field is strong enough to distort the electron clouds that surround an atom's nucleus, stretching atoms into long, thin cylinders. In this environment, chemistry as we know it ceases to exist. Molecules cannot form because the magnetic forces pulling on the individual atoms are stronger than the bonds that would hold them together. From a distance of thousands of miles, far outside the star's physical surface, this magnetic grip could tear complex matter apart atom by atom. The star's own surface is a hellscape defined by this unimaginable force. The magnetar's rigid crystalline crust, already under immense strain from the star's density, is gripped and contorted by these magnetic fields. The stress builds until, just like on a regular neutron star, the crust cracks in a starquake. But on a magnetar, this seismic event is amplified into a cataclysm of cosmic proportions. The shifting crust releases energy that violently rearranges the magnetic field lines anchored to it. In a process called magnetic reconnection, these lines snap and reconnect, unleashing a torrent of energy. The result is a giant flare. For a fraction of a second, this single star can emit more energy than our Sun will produce in its entire 10 billion-year lifetime. From across the galaxy, such a flare would momentarily outshine every star in the Milky Way combined, a blinding flash of X-rays and gamma rays. In 2004, a magnetar flare from 50,000 light-years away was so powerful it actually compressed Earth's magnetic field and ionized our upper atmosphere. A palpable magnetic sigh felt across the solar system. To witness such an event from even a few light-years away would be to see a second sun ignite and die in the sky, a final testament to a force that can twist the fabric of reality itself. A magnetar's flash is a localized apocalypse, but to find true cosmic emptiness, you must zoom out to the largest scales of reality. The universe is not a uniform soup of stars, it is a vast cosmic web with brilliant filaments of galaxies surrounding immense dark voids. The grandest of these empty spaces is the Boötes void, a spherical region of near-nothingness so large it defies belief. Stretching approximately 330 million light-years across, This void is a hole in the fabric of the cosmos, a bubble of profound isolation. If you placed our Milky Way at its center, you would have to travel for tens of millions of years at the speed of light in any direction before you would encounter another major galaxy. The few galaxies that do exist within this void are not clustered together, but scattered like lonely islands in an endless, dark ocean. The environment here is one of ultimate scarcity. The density of matter is so low that the space between these isolated galaxies is not merely empty. It is a vacuum far more perfect than anything we could ever create in a laboratory on Earth. From within one of these lonely island galaxies, the night sky would be a source of terror, not wonder. Instead of a glittering tapestry of nearby stars and the faint smudge of the Andromeda galaxy, the sky would be almost perfectly black. Only a handful of faint, distant pinpricks, the other void galaxies, would break the darkness. The Milky Way's own band of light would be your only constant companion, a reminder of your own isolated stellar city. For generations, astronomers living in such a place might believe their galaxy was utterly alone in the universe, the sole bastion of light in an infinite, empty night. The existence of the Boötes void challenges our understanding of how the universe evolved after the Big Bang. One leading theory suggests it is not a single void, but the merging of several smaller voids, a cosmic accident of distribution on a staggering scale. Another, more speculative idea is that it could be evidence of something even more profound, like the imprint of an early universe phase transition, a scar frozen into the structure of spacetime itself. Whatever its origin, the void stands as a humbling counterpoint to the vibrant, crowded galactic clusters. It is a reminder that for all the violent, energetic extremes we have explored, the universe also holds an opposite pole, an environment defined not by an excess of force, but by a devastating, almost absolute lack. The profound emptiness of a cosmic void is a terrifying thought, but it pales before the focused, inescapable pull of a cosmic singularity. The environment just outside a black hole's event horizon is a theater of such extreme physics that it feels less like science and more like a nightmare. This invisible boundary marks the point of no return, where the escape velocity exceeds the speed of light itself, but the true horror begins before you even cross it. As you fall feet first toward a stellar mass black hole, the difference in gravity between your head and your feet becomes catastrophically significant. The force on your feet, being slightly closer to the black hole, becomes immensely stronger than the force on your head. This tidal force doesn't just pull, it stretches. You would be elongated into a thin strand of atoms, a process scientists grimly and accurately call spaghettification. It is a violent, physical unraveling where every molecule in your body is pulled along a line toward the central point of infinite density. For supermassive black holes like the one at our galaxy's center, the event horizon is so far from the core that these tidal forces are weaker at the boundary, meaning you might cross it intact, only to be shredded later in the depths. But for a smaller black hole, you become a human streamer long before you reach the point of no return. Time itself becomes a chaotic element here. To a distant observer watching your fall, you would appear to slow down, freezing in a red-shifted haze just at the event horizon, an image that would fade over eons. For you, however, time would seem to pass normally as you fell inward, while the entire future history of the universe outside would flash before you in a blinding rush of accelerated light. The space around you is warped beyond recognition, twisted into a maelstrom where the very concepts of forward and backward lose meaning. All paths lead inward. It is the ultimate extreme environment, not for its heat or pressure, but for its absolute negation of the rules that govern everywhere else. The event horizon is a one-way door where the universe as we understand it simply ends, and what lies beyond is a mystery that our current physics can only describe with the chilling blank of a mathematical singularity. Yet the crushing silence of a black hole's boundary is not the only story. In a neighboring galaxy, a different kind of cosmic violence is at work, one that builds rather than destroys. The Tarantula Nebula, a sprawling cloud of gas and dust in the Large Magellanic Cloud, is the universe's most prolific stellar nursery, a place where creation itself is a violent, overwhelming event. This is not a gentle cradle, it is a chaotic, radiant forge. At its heart lies the star cluster called R136, a dazzling and crowded metropolis of stellar giants. Some of these young stars are true behemoths, over 250 times the mass of our Sun, and they burn with a ferocious blue-white intensity. Their environment is one of relentless energy. These titans flood the surrounding nebula with a blistering torrent of ultraviolet radiation, so powerful it ionizes the gas for hundreds of light years, causing the entire cloud to glow with an eerie, beautiful luminescence. But that light is a side effect of a more physical force. The hurricane-like stellar winds these stars blast into space. These are not breezes, but supersonic rivers of charged particles that slam into the surrounding gas clouds with the force of countless explosions. The winds act like cosmic sandblasters, sculpting the nebula's material into vast, dark pillars and intricate filaments, compressing some regions while eroding others away. And then the thunder arrives. The most massive stars live fast and die young, exploding as supernova within just a few million years. In the Tarantula, these explosions are not rare endings, they are a constant shaping rhythm. Each detonation sends a titanic shockwave racing through the nebula at thousands of kilometers per second. When this wall of force slams into a dense, cold pocket of gas and dust, it does not simply scatter it. The shockwave compresses it, triggering a gravitational collapse that can ignite a whole new generation of stars. It is a breathtaking cycle of death and rebirth, where the explosive end of one star becomes the violent, necessary birth cry for dozens more. To witness this region from a hypothetical nearby planet would be to live in a sky of perpetual fireworks, lit by the glare of stellar giants and shaken by distant, rumbling booms that signal both an end and a beginning. This nebula shows us that the universe's most extreme environments are not always tombs. They can also be cradles where chaos and destruction are the essential tools for building the next chapter of the cosmos. The fiery forges of the Tarantula Nebula sculpt stars from chaos, but in the deep freeze of the outer solar system, a different kind of world building is underway. Saturn's largest moon, Titan, is a world shrouded in a thick orange haze, a place where familiar earthly processes play out with utterly alien ingredients. Its atmosphere is primarily nitrogen, just like Earth's, but it is 4 times denser at the surface, a soupy blanket that presses down with a weight you could feel on your skin. This haze hides a surface so cold it makes Antarctica feel tropical, with temperatures plunging to a staggering -179 degrees Celsius. At this deep freeze, water is harder than granite, and the rocks are actually made of water ice. Yet, this frozen world is far from dead. It possesses the only known stable liquid lakes and seas on the surface of any world besides Earth. But these are not bodies of water. On Titan, the liquid is methane and to a lesser extent ethane. Here, the simple hydrocarbons that are gases on our world become the rains, rivers, and oceans of an alien hydrological cycle. The sun's feeble heat at that distance is enough to slowly evaporate liquid methane from the lakes. It rises, forms clouds in the thick nitrogen sky, and then falls back to the surface as a slow, chilling rain of liquid natural gas. This methane rain carves river channels through the icy landscape, erodes shorelines, and fills vast polar seas. The largest of these, Kraken Mare, is a hydrocarbon sea larger than Earth's Caspian Sea. Imagine standing on its frigid shore under a dim, orange sky. You would see gentle waves lapping against an ice rock beach, but the fluid would be clear as glass, and its density is so low you could probably wade through it with ease, though you would instantly freeze solid. The smell, if you could smell in a spacesuit, would be absent as these compounds are odorless. This creates an environment of profound paradox, a landscape that looks hauntingly familiar with dunes, mountains, and shorelines, yet is composed of materials and governed by a chemistry that is utterly foreign. It is a place where the very concept of a river is divorced from water, proving that the processes that shape planets are not unique to our own. They are universal principles waiting for the right ingredients, no matter how strange, to bring them to life. Titan's gentle methane rains fall in a profound, cold silence, but the skies of its parent planet roar with an invisible, lethal fury. Jupiter's magnetosphere is not merely a magnetic field, it is a colossal, dynamic force field that dwarfs every other in our solar system. If you could see it, it would appear larger than the full moon in our sky, a teardrop-shaped bubble of influence stretching millions of miles into space, powerful enough to deflect the solar wind itself and shield its many moons. But within this vast magnetic shield lies a trap of unimaginable intensity. Jupiter's rapid rotation, its massive size, and the volcanic activity of its moon Io, which spews sulfur and oxygen into space, combine to create the most powerful radiation environment we know. Charged particles, electrons and protons accelerated to nearly the speed of light, are captured by the magnetic field lines and forced into a frenzied, spiraling dance around the planet's equator. These are the radiation belts, and they form a donut-shaped cage of pure energy around Jupiter, millions of times more radioactive than Earth's protective Van Allen belts. The dose here is not measured in millisieverts but in sieverts per hour, a level that would deliver a fatal dose to a human in mere minutes. For any unprotected electronics, it is a realm of instant death. The high-energy particles slam into microchips and sensors, causing bit flips, frying circuits, and degrading materials in a process called radiation poisoning for machines. The Galileo spacecraft, which spent years orbiting Jupiter, had to be specially hardened with lead and tungsten shielding, and even then, its camera and instruments suffered over 100,000 detectable radiation hits. To venture into the heart of these belts is to sail into the most intense particle accelerator in the solar system, a natural environment where the very fabric of space crackles with a destructive energy that is both invisible and absolute. It is a reminder that some of the universe's most extreme environments offer no spectacular visuals, just a silent, omnipresent sizzle that means certain death for anything we might send to explore it. Jupiter's radiation belts are a silent, invisible inferno, but some planets face a far more visible and ancient form of fury. Orbiting perilously close to their suns are the lava worlds like Kepler-10b and Ko-Ro T7b. These are not merely hot planets, they are worlds where the very concept of a solid surface has been erased by stellar proximity. Imagine a place where the sun does not rise or set. It is a fixed, blazing monstrosity that dominates half the sky forever. One hemisphere of these tidally locked planets is in permanent, scorching daylight, while the other might dwell in a perpetual, scorching twilight, heated by global winds of unimaginable ferocity. The surface temperatures on the day side soar beyond 2,000 degrees Celsius, hot enough to vaporize iron and turn rock into liquid. The landscape, if you could call it that, is likely a global ocean of magma, a churning, incandescent sea of molten silicates stretching from horizon to horizon. The waves on this ocean would be sluggish, viscous ripples of liquid rock, and its tides would be pulled not by a moon, but by the immense gravity of the star itself. Some models suggest that in this hellish crucible, a bizarre form of geology might occur. Just as icebergs of water ice float on our oceans, continental landmasses of lighter, solidified lava might form on the magma sea. These would not be granite continents, but rafts of minerals with a higher melting point that crystallized out of the global melt. They would float on the denser molten rock beneath, slowly drifting and colliding in a tectonic dance of fire. The atmosphere of such a world is another layer of nightmare. At these temperatures, the surface lava would be actively boiling, evaporating rock vapor into the sky. The thin, tenuous air might be composed of vaporized silicon, sodium, iron, and other elements that are solid rock on Earth. At night, this metallic vapor could condense and fall as a gentle rain of tiny mineral droplets or even snowflakes of stone, only to be remelted at dawn. These planets are the end result of a cosmic dare, a test of how close a world can orbit its star before it is completely unmade. They show us the raw geological infancy of rocky planets, a phase Earth itself passed through billions of years ago, frozen in time and amplified to a horrifying, beautiful extreme by an unblinking sun. The lava worlds are defined by the violent heat of a nearby star, but the universe holds an opposite extreme, a cold so profound it defies the very background temperature of creation. The Boomerang Nebula, a ghostly bow tie of glowing gas located 5,000 light-years away, is officially the coldest known place in the natural universe. Here, the temperature plummets to a mere 1 degree above absolute zero, a chilling -272 degrees Celsius. This is even colder than the faint, pervasive afterglow of the Big Bang, which fills all of space at about -270.4 degrees. So how can a place in space be colder than the leftover heat from the birth of everything? The answer lies in a stellar death that chose a particular path of violent expansion. The Boomerang is a pre-planetary nebula, a brief and dramatic phase in the life of a low-mass star like our Sun. In its final act, the star is not exploding, but rather shedding its outer layers in a fast, steady wind. The central star here, however, is ejecting material at a staggering speed, over 150 kilometers per second, which is about 10 times faster than similar dying stars. This rapid expulsion acts like a cosmic air conditioner. You can feel this principle yourself by blowing air over your hand with your mouth wide open. The air feels warm. Now purse your lips and blow. The air feels cooler. That is because the fast-moving air causes rapid expansion and cooling. In the Boomerang Nebula, that process is amplified to a universal scale. The gas is expanding into the near-perfect vacuum of space so quickly that it cannot absorb heat from anywhere, not even from the faint warmth of deep space itself. It is a natural, runaway refrigerator. The result is a nebula where molecules move with agonizing slowness, their kinetic energy almost completely drained. This extreme cold has a visible effect. It allows astronomers to study the nebula's structure in remarkable detail because the frigid gas absorbs the faint microwave background radiation from the universe, casting a shadow we can detect. This eerie, symmetric cloud is a fleeting monument to a star's final, chilling breath, a pocket of space where the expansion of gas has created a deeper cold than the universe has known since its first moments. It is a sobering reminder that even in the vastness of space, local conditions can create pockets that are more extreme than the cosmos' own baseline, crafting a silence and a stillness more absolute than the void between galaxies. The Boomerang Nebula holds a record for cold, but on the opposite side of the temperature spectrum lies a world where the wind itself is a weapon of mass erosion. The exoplanet HD 189733b is a hot Jupiter, a gas giant orbiting so close to its star that a year lasts just 2.2 Earth days. This proximity has baked the planet into a permanent, violent state, and its most defining feature is not its heat, but the unimaginable storms that heat creates. Because it is tidally locked, one side of the planet forever faces its star in a blistering 2,000 degrees Celsius glare, while the night side languishes in a relative deep freeze of around 700 degrees. This extreme temperature difference, over 1,000 degrees Celsius from one hemisphere to the other, acts like a planetary scale engine. The searing hot air on the day side expands and rises with explosive force, rushing toward the cold night side in a desperate attempt to equalize the pressure. What results are not breezes but supersonic torrents. The winds on this world scream at speeds exceeding 5,400 miles per hour, over 7 times the speed of sound on Earth. To stand in such a gale, if you could stand at all, would be an experience of pure, annihilating force. The sound barrier would be broken not by a craft, but by the air itself, creating a perpetual, deafening sonic boom that resonates through the entire atmosphere. And this wind carries a horrific payload. The extreme heat on the day side vaporizes silicate minerals, the compounds that make up glass and sand on our world. These particles are swept up into the supersonic flow, where they condense into tiny, razor-sharp shards. The planet does not experience rain as we know it. Instead, it endures sideways, hypervelocity storms of molten glass. These are not gentle droplets, but a scouring, abrasive hail moving faster than a rifle bullet, capable of stripping the surface off any solid structure in moments. The entire world is caught in a perpetual global hurricane of cutting fury, a tempest where the very sky is an enemy. This is an environment where weather is not a temporary condition, but a permanent, abrasive state of being, sculpting the planet's atmosphere into a hellish maelstrom of heat, sound, and slicing silica. Those supersonic glass storms are a planetary-scale sandblaster, but gravity itself can sculpt light on an even grander canvas. When we look at the most massive structures in the universe, galaxy clusters containing thousands of galaxies trillions of times the mass of our Sun, we are not just looking at a collection of objects. We are looking at a lens. The combined gravity of all that dark matter and countless stars warps the very fabric of space-time around the cluster, creating a colossal, natural distortion in the path of light. This phenomenon, predicted by Einstein, is called gravitational lensing. It means the cluster's immense gravity bends the light from galaxies far behind it, acting like a flawed cosmic magnifying glass. For the most perfectly aligned background galaxies, this bending can create breathtaking Einstein rings, where the distant galaxy's light is smeared into a complete circle of fire around the foreground cluster. But the true extremes of this environment are found along razor-thin lines within the lens called caustics. These are not physical structures, but theoretical boundaries of infinite magnification within the gravitational map. Think of them as the focal lines of this imperfect lens, where the warping of space becomes so precise and concentrated that the light from a single background star can be amplified thousands of times. Crossing a caustic line is like stepping through a funhouse mirror that multiplies your reflection. A distant star, which would normally be far too faint to see, can suddenly flare into visibility as its light is focused and split into multiple images by the cluster's gravity. We have witnessed this with individual stars nicknamed Icarus and Earendel, whose light was magnified by caustics to make them the most distant single stars ever observed. The environment at a caustic is one of ultimate distortion. It scrambles our view of the distant universe, stretching single galaxies into long, luminous arcs and creating multiple, ghostly copies of the same object arranged in a perfect geometric pattern around the cluster's center. This is not an illusion, it is a direct map of how mass warps reality itself. By studying these extreme distortions, astronomers can literally weigh the invisible dark matter holding the cluster together, using warped light as their scale. It is a place where gravity does not just pull on matter, it rewrites the sky, turning the most massive objects in existence into telescopes that show us the deepest reaches of time. Gravity may warp the light of distant galaxies, but our own star unleashes a fury that shapes the very space around us. The Sun's corona is its outer atmosphere, a shimmering, pearly white halo visible only during a total solar eclipse. This beautiful veil, however, hides the solar system's greatest thermal mystery. The visible surface of the Sun, the photosphere, simmers at a toasty 5,500 degrees Celsius. Yet, just a few thousand kilometers above it, in the wispy corona, the temperature skyrockets to over 1 million degrees. It is as if you walked away from a campfire and the air around you suddenly became thousands of times hotter than the flames. This coronal heating problem has baffled scientists for decades. How does the Sun's atmosphere become so unimaginably hot? The leading suspect is the Sun's tangled, dynamic magnetic field. The photosphere is not a calm surface. It seethes with convection like a pot of boiling water. This motion churns the magnetic field lines anchored below, twisting and braiding them into complex knots that rise into the corona. Think of these magnetic lines as incredibly taut rubber bands. When they become too twisted, they can suddenly snap and reconnect in a process that releases colossal amounts of energy, heating the surrounding plasma in nanoflares, tiny but ubiquitous explosions. Another theory points to powerful magnetic waves generated by the turbulence below that travel upward and dissipate their energy as heat in the thin corona. The environment they heat is one of magnetically confined plasma, a fourth state of matter where gas is so hot its atoms are ripped apart into a soup of charged particles, electrons, and ions. This superheated plasma is trapped and shaped by the Sun's magnetic architecture, forming beautiful loops and streamers that follow invisible field lines. But not all of it stays confined. The corona's immense heat gives the plasma such energy that the Sun's gravity cannot hold it all. This creates the solar wind, a constant, supersonic stream of charged particles blowing outward in all directions, bathing every planet in a faint but persistent breeze. This wind is the very breath of the solar system, carrying the Sun's magnetic field with it to the edge of interstellar space. Sometimes, however, the Sun does not breathe, it screams. When particularly complex magnetic regions become unstable, they can trigger the solar system's most violent storms, coronal mass ejections. These are not mere flares of light, but billion-ton eruptions of magnetized plasma launched from the corona at speeds exceeding 1 million miles per hour. A single one of these events contains the energy of thousands of nuclear bombs detonating every second for over a week. When a coronal mass ejection is aimed at Earth, its arrival days later can compress our planet's magnetic shield, triggering dazzling auroras but also posing a severe threat to satellites, power grids, and astronauts. The corona, therefore, is not a passive halo. It is a seething, magnetically dominated furnace whose mysteries directly impact our technological civilization. A reminder that the most extreme environment in our neighborhood is the one that gives us life and could one day temporarily take our modern world away. Far from the Sun's searing corona, in the frozen stillness of the solar system's edge, lies a world that redefined itself before our eyes. Pluto's heart is not a metaphor, but a real geological feature, a vast, pale basin named Sputnik Planitia. This is a glacier, but not of water. It is a slowly churning sea of solid nitrogen, mixed with traces of methane and carbon monoxide ice, flowing in slow motion over a timescale of millions of years. The temperature here is a brittle -230 degrees Celsius, so cold that nitrogen, which makes up most of our air, freezes solid as rock. This heart beats with a subtle geological rhythm, its surface divided into irregular polygonal cells by convection currents rising from Pluto's slightly warmer interior, a sign that even this distant dwarf planet is not entirely geologically dead. But framing this frozen nitrogen plain are mountains, and these highlands tell an even stranger story. They are not made of rock as we know it. At Pluto's profound temperatures, water ice is no longer a slippery substance. It achieves the structural strength of granite. These towering peaks are literally mountains of water ice, as hard as steel, glinting under a sun that appears only as a very bright star in a perpetually twilight sky. And upon these frozen slopes, New Horizons spacecraft saw something puzzling, dark, reddish patches staining the bright ice. This is where the environment becomes truly alien. Scientists suspect these stains may be tholins, complex organic molecules created when methane and nitrogen in Pluto's thin, hazy atmosphere are cooked by the faint solar and cosmic radiation, eventually falling as a kind of cosmic soot onto the surface. But the methane itself may be part of the very ground. There is a compelling possibility that Pluto's crust, especially in these rugged highland regions, contains vast reserves of methane clathrate. A clathrate is a cage, a lattice of water-ice molecules that forms under high pressure and low temperature, trapping other gases inside its crystalline structure. On Pluto, methane molecules could be imprisoned in these icy cages, creating a substance that looks like ordinary water ice but holds a volatile guest within. This creates a bizarre, frozen desert landscape. Imagine a windswept dune field, but the dunes are made of sand-sized grains of methane ice or methane clathrate, blown across the water ice bedrock by Pluto's extremely thin but existent nitrogen winds. The entire landscape would be a study in surreal stillness, where the very ground you stand on is a volatile compound held in stasis by the deep cold, waiting for a change in temperature or pressure that might never come. It is a world built not from rock and lava, but from ices we consider transient gases, a testament to how chemistry and geology merge into one when the thermostat is turned almost all the way down. That profound cold on Pluto is a local whisper, but the entire cosmos is filled with a deeper, older chill. The universe itself is immersed in a bath of relic radiation, a faint afterglow from its fiery birth. This is the cosmic microwave background, and it is the oldest light we can possibly see, a snapshot of the universe when it was just 380,000 years old. Before this moment, the cosmos was a dense, opaque plasma, too hot for light to travel freely. As it expanded and cooled, protons and electrons finally combined to form neutral hydrogen atoms, and the universe suddenly became transparent. That first flash of light, once blazing hot, has been traveling for over 13.8 billion years. In that time, the expansion of space itself has stretched those photons from visible light into the microwave part of the spectrum, cooling them to a mere 2.7 degrees above absolute zero, a frigid minus 270.4 degrees Celsius. This radiation is not coming from one point in the sky. It is everywhere, a uniform sea of microwaves that fills every cubic centimeter of the universe, including the room you are in right now. It is the most pervasive extreme environment of all, the baseline temperature of empty space. Yet this uniform sea holds the most important wrinkles in history. When we map the cosmic microwave background with incredible precision, we find it is not perfectly smooth. There are tiny variations in temperature, minute fluctuations on the order of 1 part in 100,000. These are not random defects, they are cosmic fossils. These faint hot and cold spots represent regions of slightly higher and lower density in the infant universe, the gravitational seeds planted by quantum fluctuations in the first fraction of a second after the Big Bang. Every galaxy cluster, every void, every filament in the cosmic web we see today grew from these microscopic imperfections. That map of the microwave sky is therefore a blueprint, a prenatal photograph showing the potential for all structure, from the smallest dwarf galaxy to the largest supercluster. We are literally seeing the imprint of the universe's first moments, a pattern frozen in microwave light that dictated where stars would eventually shine and where eternal darkness would reign. It is the ultimate origin story, written not in rock or ice, but in the subtle warmth of ancient light. The faint glow of the cosmic microwave background is the universe's oldest whisper, but some stars scream their existence with a violence that shakes galactic space. Hypergiant stars like VY Canis Majoris are not merely large, they are cosmic titans operating at the very edge of physical possibility. If you placed this star at the center of our solar system, its surface would extend beyond the orbit of Jupiter, engulfing every inner planet. Yet, despite this staggering volume, its mass is only about 30 times that of our Sun. This creates a star of astonishingly low density, a vast, tenuous balloon of plasma held together by a whisper of gravity. The environment on such a star is one of profound instability. Its surface is not a defined boundary, but a churning, turbulent fog of superheated gas. Gravity here is so weak at the outer layers that the star can barely hold onto its own atmosphere. This leads to the hypergiant's most dramatic trait, its catastrophic mass loss. These stars blast away solar winds of unimaginable scale, not the steady breeze of our sun, but a continuous hurricane-like eruption. V. Canis Majoris ejects the equivalent of Earth's mass in gas and dust every single year. Over millennia, this relentless expulsion builds a vast, chaotic nebula around the star, a glowing shroud of its own shredded body that stretches for light years. This nebula is not a serene cloud, it is a storm front of condensing dust and billowing gas, lit from within by the star's furious radiance. The star itself pulses and convokes, brightening and dimming as it struggles to maintain equilibrium between the outward push of radiation and the inward pull of its own waning gravity. This is a star living on borrowed time, and its end is written in its very turbulence. Hypergiants are doomed to die as supernova, and when one like Betelgeuse finally exhausts its fuel, its core will collapse. The resulting explosion will, for a few glorious weeks, outshine every other star in the Milky Way combined, visible even in our daytime sky. That final flash will be the star's last act of extreme self-expression, a cosmic declaration so brilliant it will, for a moment, drown out the light of 100 billion neighbors. A hypergiant's final supernova is a cosmic spectacle we can at least describe, but there is one environment where our very language of description fails completely. At the very heart of a black hole, past the event horizon and beyond the point of spaghettification, lies the ultimate extreme, the singularity. This is not a place you can visit, not a thing you can see. It is a mathematical boundary where the elegant equations of Einstein's general relativity scream in protest, yielding results of infinity. Within the singularity, all the mass of the collapsed star is crushed into a point of zero volume, creating a condition of infinite density. Here, the very concepts of space and time as we understand them cease to exist. They are not merely warped, they are torn apart, merged into a single, undifferentiated fabric where cause and effect have no meaning. To speak of a location or a moment at the singularity is meaningless, for the rules that define here and there, before and after, simply do not apply. Our physics, which has guided us through neutron stars and magnetars, breaks down entirely. To probe further, we must venture into the realm of theoretical speculation, to scales so small they defy imagination. This is the Planck scale, a domain where the smooth geometry of spacetime predicted by relativity is believed to dissolve into a seething, chaotic quantum foam. At this level, space and time themselves might be quantized, emerging from a froth of fleeting wormholes and virtual particles. Some theories suggest the singularity might not be an end, but a bridge, a tunnel in spacetime known as an Einstein-Rosen bridge, or more popularly, a wormhole. In this speculative picture, the crushing gravity of the singularity could theoretically puncture a hole through the fabric of reality, creating a shortcut to another point in our universe, or even a gateway to an entirely separate cosmos with its own physical laws. Yet, this remains a mathematical possibility, not an observed reality. The environment of a singularity is the final, absolute frontier of human knowledge. It represents the edge of the map where our most brilliant theories dissolve into infinite mystery. It forces us to confront the humbling truth that for all we have learned about the universe's most violent and beautiful extremes, the deepest heart of creation remains, for now, a perfect and profound unknown. From the boiling supercritical oceans of distant worlds to the silent, infinite mystery of a singularity, our journey has spanned the cosmos's most unimaginable frontiers. We have seen planets where diamonds fall from the sky and stars that crack their own crystalline crusts in magnetic tantrums of pure energy. Each of these environments, from the desolate rogue planets to the screaming jets of galactic cores, represents a laboratory of extremes where the ordinary rules of physics are not just bent but shattered and rewritten. They push the boundaries of what we thought possible, forcing our science and our imagination to stretch into terrifying and beautiful new shapes. Yet, in studying these places of ultimate hostility, we are not merely cataloging cosmic curiosities. We are deciphering the universe's fundamental language. The same physics that creates a hypervelocity star or a magnetar's flare governs the gentle spin of our own planet and the warmth of our sun. By probing the limits, we better understand the center. We learn that chaos and order, creation and destruction are not opposites, but partners in an eternal dance that has built everything we see. So the next time you look up at the night sky, remember that the quiet darkness is an illusion. It is filled with invisible storms, ancient light, and the silent, grinding work of forces beyond human scale. Which of these extreme environments left you the most awestruck? Was it the idea of a sunless ocean on a wandering world, or the quantum storms inside a dying star? Let us know in the comments below. If you want to keep exploring the universe's greatest mysteries with us, be sure to subscribe. Until next time, keep looking up. There is always more wonder to